Welcome to chapter 4, part 2. In this part, we're going to go over variance and then two particular discrete random variable and then their distributions. So for variance, we're going to start with its definition. Okay, so recall that we have covered the expectation or expected value or mean using this notation. Okay, E of x as x is the random variable. Okay, a lot of times we also use mu to represent the mean. It is the weighted average of the possible values of x. Okay, we covered the definition and how to compute it. So now, another very important aspect of any random variable is its variance. Okay, it measures the variation or spread of these values that the possible values that the random variable can take. Specifically, we use this notation sigma square to represent the variance. Okay. And then we also write VAR stands for variance and then parentheses of the random variable. The definition goes in this way. So as you can see, we're looking at the expectation, okay, of any possible values of x, okay, of its distance between its mean, okay, and then we take the square, okay. So what this is saying is that we are considering the variation in a particular way that we're looking at x, which is say one possible values of capital X, okay? We're looking at the distance of that from its mean, okay? We take the square of it, and then we take the whole thing of the expectation, okay? So we call this as the variation, okay? Again, a variance, again, is measuring the variation of these values. And then the variation is talking about the distance, square distance between the values with its mean. Okay, so since we use EX and also or mu to represent the mean, so sometimes it's also written in this way. Okay, so here we want to highlight that this holds for all random variables. It does not have to be discrete random variable, what we cover in this chapter. So this definition holds for continuous random variables as well, as later we're going to see in chapter 5. Okay, the definition itself hopefully is intuitive and makes sense to you. But in terms of computing the variance, we actually always use a simple simplification. Okay, and what this is saying is that the variance, okay, of a random variable x actually can be simplified. Instead of going back to the definition to compute this way, you can do it as the expectation of x squared minus mu squared. Okay, so you might be wondering, okay, why are we able to do that? Okay, so if we come back to this definition really quick here, okay, so the expectation, okay, of x minus mu squared, okay, the expectation is taken with respect to x, okay, so keep that in mind. And then we can always, since it's expectation, we can go back to the definition of expectation in the first place. But before that, let's expand the square term, okay. Okay, all right, so we expanded the square term is x squared minus 2x mu plus mu squared. All right, like I said, the expectation is taken with respect to x, okay? So here we have a linear function of x and x squared in this case. So we can further simplify this by, let me just write it maybe even more in even more detail here. We're going to do expectation of 2x mu, okay, and then plus the expectation of mu squared, okay. All right, so to further do this, okay, keep in mind our properties of expectation, okay. So here mu is a constant, okay, because the expectation is taken with respect to x. So if it's a constant, multiply with a random variable, also the 2 is a constant. So we can actually bring out that 2 mu outside of the expectation, okay? And then of course, like I said, mu is a constant, so mu square is also a constant, so this becomes just mu squared. Okay, so the last step to see why the common simplification works is to see this part, okay? So 2 mu expectation of x. Remember, expectation of x, we also use mu to represent it. So this whole thing actually becomes 2 mu squared, okay? So this becomes 2 mu squared, okay? We minus 2 mu squared plus 1 mu squared. So all this whole thing becomes the expectation of x squared minus mu squared, okay? So that's why you see we have just shown why this common simplification works, okay? And then once we know this, like I said, it could be much simpler if you use this common simplification to calculate the variance instead of going back to the definition and then do it every time, okay? All right, so keep that in mind, okay? And with variance, we actually also ready to introduce what we call standard deviation, okay? So the standard deviation actually pretty straightforward. It's just the square root, okay, of the variance, okay? We use sigma to represent the standard deviation. And remember earlier, we used sigma squared to represent the variance. So pretty much sigma, like we're saying over here, is the square root of the variance. And for calculation, once you know what the variance is, you're able to compute the standard deviation. So let's go over with an example. Compute the standard deviation of a fair four-sided diagonals, okay? So just keep in mind, we always have our handy result. Like I said earlier, the common simplification of the variance is this, okay? Okay, and then of course, we're asked to do the standard deviation. So once you get the variance, take the square root, you're able to go back to the standard deviation, okay? So remember, since we know this common simplification, what we need to do is we need to compute the expectation of the x squared, okay? And also the expectation of x. And then from there, we'll be able to get the variance and then get the standard deviation. So for us, just to keep in mind, we're working with a fair four-sided die toss, okay? So the probability, or I should say the PMF, okay, of this random variable, okay, is that x can take 1 with probability 1/4, okay? X could be 2 with probability 1/4, okay? Same goes for 3 and 4, okay? Because it's a fair die, we get all of them to be 1/4 as the probability. And once we have written all of this out, we know the PMF of this random variable, okay? All right, so with all that, and then going back to what we learned from previously about the expectation and how to calculate it, we are able to go with the expectation of x, okay, is 1 times 1/4 plus 2 times 1/4 plus 3 times 1/4 plus 4 times 1/4, which is 2.5, okay? And then for the expectation of x squared, okay, simply this is following, if you remember, the result, what we covered before about the expectation of a function of x or a function of random variable. So pretty much we know the PMF, okay? And then we only need to multiply the PMF, like the each probability with x squared value, okay? To do that, you would do 1 times 1/4 times 2 squared, right? Times 1/4 times plus 3 squared over 4 and then 4 squared over 4. So with that, you're gonna get 7.5 as the expectation of x squared. So following this result, okay, we're able to get the variance, which is 7.5 minus 2.5 squared, because we need to square the expectation, which is 1.25. And then lastly, we know that the standard deviation definition is square root of variance. So we simply take the square root of 1.25 to get 1.12 as our standard deviation for this result, okay? So this is a demonstration of telling how to actually calculate the variance, use the common simplification, okay? And then from there, we're able to get the standard deviation. So lastly, for this part, I wanted to also cover that the variance, like we said it earlier, that variance measures the variation or the spread of the random variable. So I wanted to use an example to show you what we mean by that. Okay, so here, let's just say we have 2 random variables. Okay, both of them discrete. We're showing you the PMF. Okay, so the only difference, as you can see, between the two is that x1 can take -1 and +1. Each with 50% chance, okay? So that's the PMF. X2, we can take -2 and +2, and then each of which is having a probability of 50%. So if we do the math, okay, I will encourage you to try it out to make sure that that works for you. we can show that the mean of x1 is actually 0, and the standard deviation, or like I should say this, the variance of x1, which we use sigma 1 squared, if we do the math, it's going to be 1, so the standard deviation is 1, okay? If we do that for x2, following the same procedure that we showed earlier, we can get the mean also is 0, and then the standard deviation to be 2. Okay, so clearly, these two random variables, even though they have the same mean, but they have different standard deviation. And in particular, the second random variable x2 is have twice as much as the standard deviation compared to the random variable x1. Okay, so increasing, like we're saying that variance measures the spread of x. Okay, so the larger the variance or the standard deviation, the higher the spread. Okay, meaning that the random variable is further, or I should say like spread over a wider interval. So if we actually do what we call like a density plot with like a bar plot over here, I should say, is that if we're doing the px, which is PMF on the y-axis, okay, and then the x-axis is just the possible values of the random variable, then you can see that, well, x1, the two possible values, both of them are at 50% PMF value, right? But then they're closer, whereas x2, they're further away. So if you, well, I didn't include the x-axis over here, but this value is -1, this is +1. Okay, this is -2, this is +2. Okay, so following that, we can see that, yes, both of them are centered at 0. Okay, once we compute the mean, but then x2 is having a wider spread than x1, which is not only shown on this graph, but also mathematically, we can see that we have a twice as large as the standard deviation of the second compared to the first. Okay, so just so you know, there are all kinds of distributions out there with standard deviation equals to 1. Okay, the example that we have earlier was on the top. Okay, but then maybe some of you know about this normal distribution, which we also going to cover in chapter 5, is continuous random variable. Okay, and the standard normal distribution actually also has the standard deviation as 1. And other distribution, like the third one down here, so the middle one is the standard normal. Okay, the third one, the bottom one, which is a right skew distribution. Okay, and it also happens to have standard deviation of 1. Okay, so all of them measured by the standard deviation is 1, meaning that they have the same level of spread. Okay, but then of course the mean could be different. I guess the first and the middle one, both of them have mean as 0 because it's symmetric, whereas the last one is probably having a slightly smaller mean because it's tilted towards this side. Okay, so this wraps up our discussion about what variance is, what standard deviation is, and what variance is measuring. Again, variance is measuring the spread or the variation of the random variable.